Hello and welcome back. In the last class, we were doing states of matter, and in that we were doing gaseous state. The last topic we did was ideal and real gas. I told you that a gas which obeys ideal gas equation under all temperature and pressure conditions is known as an ideal gas. Whereas it is observed there is no ideal gas. All gases, they are real gases. That means they obeys ideal gas equation when their volume is very large. That is when the temperature is high and the pressure is low. So when the temperature is high and the pressure is low, they obey ideal gas equation, this equation. But if the reverse happens, the temperature is low and the pressure is high, when their volume reduces, they start deviating from this ideal gas equation. Such gases, they are known as real gases. Now, if a gas is not obeying ideal gas equation, that means it is not obeying Boyles law, Charles law, and Avogadro's law. The deviation from Charles law is not considered as a deviation. Because according to Charles' law, for every 1 degree rise in temperature, the volume of a given mass of a gas should increase by 273rd part of its volume at 0 degree. Suppose the volume is not increasing by 273rd part, it is increasing by 274th part or 275th part or 270th part. The volume is increasing. So we cannot consider it as a deviation. Likewise, according to Avogadro's law, under the condition of standard temperature and pressure, 22.4 liters of all the gases should have 6.023 into 10 to the power 23 molecules. This value is so large that if some of the molecules we plus or minus in this value, that hardly makes any difference. So deviation from Charles' law and deviation from Avogadro's law is not considered as a deviation, whereas deviation from Boyle's law is considered as a deviation, and we'll study about that. So today we'll see deviation from Boyle's law. Deviation from Boyle's law. Well, Boyle's introduced a factor that is represented by Z, and it is always equal to ratio of PV to nRT, and it is known as the compressibility factor. Now, for an ideal gas, Z should be equal to 1 at all temperature and pressure conditions, because for an ideal gas, PV is always equal to nRT. However, it is observed that for a real gas, Z is equal to 1 only when temperature is high and pressure is low. That is when the volume of the gas is very large, then only Z is equal to 1. We can plot a graph between Z and pressure for any gas. Now suppose here I am plotting a graph for gas X2. On one axis I am taking pressure, on another axis I have got Z. And suppose this is the value, here Z is equal to 1. So for any gas X, if I plot a graph, the graph can go like this. This is at temperature T1. So at temperature T1, you can see three parts of this graph. At very low temperature, at very low pressure, till this pressure, you will see Z is equal to 1. That is when the pressure is low, the volume of a gas is very large, and even a real gas is behaving like an ideal gas. Now the second component, you will see till this point, where you will see that Z is less than 1. And above this point, you will see Z is more than 1. So as the pressure increases, Z is no more equal to 1. That means the gas is deviating from ideal gas equation. This is at temperature T1. Now, if I increase the temperature, the graph will go somewhat like this at temperature T2. Likewise, at temperature T3, the graph will go like this. And at temperature T4, it can go like this. Now here in this, you'll observe that at temperature T3, at this temperature, the value of Z is nearly equal to 1, even at high pressure. Generally what happens at this pressure, you'll observe that at temperature T1 and T2, Z is less than 1, it is not equal to 1. But at temperature T3, Z is nearly equal to 1. That means this temperature T3 is the Boyle's temperature. So you should remember what is Boyle's temperature. It is a temperature of a gas at which even a real gas behaves like an ideal gas even at high pressure. So here we have got a real gas, that is X2, and at temperature T3 it is behaving like an ideal gas even at high pressure. So this is what a Boyle's temperature is. Now the question comes to our mind. Some scientists, they gave us some laws like Boyle's, Charles, Avogadro's, and we combined those laws to get ideal gas equation, that is PV is equal to nRT. Now gases, they are not following PV is equal to nRT to a very great extent. They are following PV is equal to nRT only when their volume is very large, that is at high temperature and low pressure. But when the temperature is low and the pressure is high, they deviate from ideal behavior. Why it is happening like that? Why the gases, they are not following Boyle's, Charles or Avogadro's law? Well, there was a scientist, Van der Waal, who started investigating this thing. So initially he started with a theory on which the Boyle's, Charles and Avogadro's law are based on. And that theory is known as kinetic molecular theory. So we'll see kinetic molecular theory. KMT, as it is abbreviated. We'll see the assumptions of KMT. What are the assumptions of KMT? First, every gas is made up of very small particles known as molecules. So every gas is made up of very small particles known as molecules. All the molecules of a gas are alike. So if we say molecule of oxygen, we'll always write down O2 because all oxygen molecules have a formula O2, they all are alike. All gas molecules exhibits same chemical and physical properties, and they are the properties of the gas. So students, all molecules of a gas, they exhibit same chemical and physical property. And the property which is exhibited by a gas molecule is the property of that gas. I give you one example. Say I am writing two molecules of hydrogen combines with one molecule of oxygen to give you two molecules of water. This is simply said to be a property of hydrogen and oxygen. We can say that two volume of hydrogen combines with one volume of oxygen to give you two volumes of water. So the property which is exhibited by the molecule is the property of that gas. So all gas molecules exhibit same chemical and physical property, and they are the property of the gas. Likewise, fourth, different number of gas molecules moves in different directions with different velocities. Hence, they keep on colliding with each other. So different number of gas molecules, they move in different directions with different velocities. And when they are moving in different directions with different velocities, there is every possibility that they'll collide with each other. So they keep on colliding with each other. Here I would like to add one thing, that the collision between the gas molecules are perfectly elastic. That means their momentum remains conserved. Their momentum does not decreases on every single collision, because had it been like that, the momentum would have been decreasing and finally the momentum will become zero. That means the velocity of the gas molecule will become zero. That means the gas molecule will come to a still position where they are not moving. If they are not moving, they will not collide with the wall of the container and they will not exert any pressure. That means the pressure of the gas will become zero after some time. Whereas it is not like that. You can store a gas in a container for thousands of years. If the temperature is same, you will have the same pressure, because the collision among the gas molecules is perfectly elastic. So, fifth point is collision among gas molecules is perfectly elastic. That is, the momentum remains conserved. Next assumption, due to larger intermolecular distances, the attraction among gas molecules is negligible. So in gaseous state, the distance between the gas molecules is very large. Hence, the attractive forces among them are very weak. They are so weak that they are practically said to be zero. Likewise, due to larger intermolecular distances, a gas always occupies such a large volume that the volume occupied by a gas molecule is negligible. So in gases, the intermolecular distances are so very large. The gas will always occupy such a large volume that the volume occupied by a gas molecule, which is very small, not visible to our eye, is negligible. It is so very small that as compared to the volume of the gas, which is very large, the volume occupied by a gas molecule is negligible. So these are the assumptions of kinetic molecular theory. Van der Waals worked on these assumptions and he found that two of these assumptions are faulty. Dear students, if we see on all these assumptions, it appears that all of them they are quite correct. Whereas the last two assumptions, like the sixth one, and the seventh one, according to Van der Waals, they are wrong. These assumptions are right only when the volume of the gas is very large. Whereas if the volume of the gas is lesser, the gas molecule will come closer. They will come so very close to each other that they will start attracting each other. So in that case, the attractive forces are not negligible, like it is stated in the sixth point. Due to larger intermolecular distances, the attractive forces among the gas molecules are negligible. Yeah, this is right, but only when the volume of the gas is very large. However, if the volume of the gas is lesser, these attractive forces are no longer negligible. These attractive forces, they are there to play their part. We cannot neglect them. And since we were neglecting them, that's why gases, they were obeying ideal gas equation only when their volume was very large. When their volume was lesser, they were no longer obeying the ideal gas equation. Likewise, the volume occupied by a gas molecule is negligible only when the volume of the gas is very large. If the volume of the gas is lesser, we can no longer neglect the volume occupied by a gas molecule. So these two assumptions, they were faulty and they were corrected by Van der Waals. So we'll see Van der Waals correction. Van der Waals correction. First we'll see correction of volume. Here I am writing PV is equal to nRT or PV is equal to RT for 1 mole of a gas. Correction for volume. We'll see this, student. Suppose here I've got a container and suppose the volume of this container is V liters. The volume of the container is V liters. A gas molecule is confined inside this container. Suppose this is a gas molecule O2, N2, F2, Cl2, Br2. And this gas molecule is occupying a volume B. Again, the gas molecule is confined in a container of V liter capacity. The volume of this gas molecule is B. See, actually what we were thinking, suppose a gas molecule, what you have learned till now, till your 10th standard, what you have learned, that the volume of the gas is the volume in which they are confined. The volume of the container is the volume of the gas. Suppose I am saying a gas is confined in a container of 10 liter capacity. By default, you will take the volume of the gas as 10 liters. That means the volume available for a gas molecule to move is the volume of the container. So if we have got a gas molecule in a container of 10 liter capacity, by default we think that the volume available for that molecule to move is of 10 liters. Whereas according to Van der Waals, it is correct only when the volume of the gas is very large. However, if the volume of the gas is lesser, we cannot neglect the volume occupied by a gas molecule. So the volume available for a gas molecule to move is V is actually V minus B. So we'll see that. So the volume available for a gas molecule to move will be V minus B for 1 mole of gas. And if we have got n number of mole, then it becomes V minus NB. Here B is known as excluded volume. I'm saying it is the volume occupied by a gas molecule. I'm not saying it is the volume of a gas molecule. A gas molecule is in continuous motion because of its kinetic energy. It has got very high energy, so it is in continuous motion. So whatever volume it has got, it occupies 4 times of its original volume. That means B is actually 4 into volume of a gas molecule. See students, different gas molecules, they have different radii. So they have different volume. We know that it is 4 by 3 pi r cube. And hence, the volume which they occupy, that is 4 into 4 by 3 pi r cube, is also constant. So B is a constant. It is a constant for a gas, and different gases have different value of B. Because different gases, they will have different radii. Like H2 will have different radii, methane will have different radii, carbon dioxide will have different radii. So different gases, they have different radii. Different gas molecules, they have different radii. So the volume occupied by them is different. That's why B is constant for a gas, and for different gases, we have different value of B. Now we'll see correction of pressure. Now, according to Van der Waal, the attractive forces among the gas molecules are negligible only when the volume of the gas is very large. However, if the volume of the gas is lesser, if the gas molecules, they are coming closer, they will start attracting each other. So the attractive forces are not negligible. Here I'll tell you one thing. Suppose here I have the wall of the container. This is the wall of the container. Here I have a gas molecule which is coming and striking on this wall. And it is exerting, say, a pressure of 10 Newton per meter square. This is the force it is exerting. So this is the pressure exerted by this gas molecule. Now, if a gas molecule is coming and striking on the wall of the container and exerting a force of 10 Newton per meter square, we consider that force per unit area as the pressure of that gas. It is quite right. This is how we measure pressure. The force per unit area is pressure. So here we can say the pressure is 10 Newton per meter square. But what if the volume is lesser? What if the gas molecules, they are coming closer to each other? Now suppose I have got some gas molecules here. This is one of the molecule I have got. This is another molecule I have got. This is another molecule I have got. And all these molecules, they are attracting this gas molecule toward themselves. When these gas molecules, they'll start attracting this molecule toward itself. That means the force with which it will strike on the wall will decrease. That means if I am observing at lower volume, if I am observing the pressure exerted by the gas molecule is 10 Newton per meter square, that means actually the pressure is more than that. All these molecules which are behind the gas molecule are attracting it. Then in that condition, it is exerting a force of 10 Newton per meter square. Had there been no these gas molecules, its pressure would have been more. That means the observed pressure, the pressure which we are observing, is lesser than the actual pressure. Had there been no these gas molecules, it may happen that the pressure exerted by this gas molecule would have been more than 10. It can be 11, 12, 13, 14, anything. So Van der Waal corrected it. According to Van der Waal, what pressure we are observing on the wall of the container is not the actual pressure. It is the actual pressure when the volume of the gas is very large. However, when the volume of the gas is lesser, the actual pressure is more than what we are observing. The gas molecule is exerting that pressure when other gas molecules, they are attracting it and they are reducing its force. Then it is exerting that pressure. It means its actual pressure is more than that. So what I can say is that actual pressure is actually equal to the observed pressure and the decreased pressure. Here in this case, we can say that the pressure which we are observing is say 10 Newton per meter square. And had there been no gas molecule behind it, the pressure would have been 12. That means these gas molecules which are here are attracting and decreasing the pressure by 2 atmospheres. So the decreased pressure is 2 atmospheres. We'll see the factors on which this decreased pressure depends. This decreased pressure is directly proportional to number of molecules per unit volume in bulk. Number of molecule per unit volume in bulk. That means these gas molecules which are here, which are behind the molecule which is striking. So these gas molecule, here I have written 3 gas molecule. Had there been 4, the force of attraction would have been more. Had there been 6, the force of attraction would have been still more. So more the number of gas molecule which are in the bulk, which are attracting the molecule which is going to strike on the wall of the container, the lesser will be the pressure exerted by it. So more the number of molecules of gas in the bulk, the attraction will be more, so lesser will be the pressure exerted by the striking molecule. So decrease in pressure is directly proportional to number of molecule per unit volume in the bulk. Likewise, decreased pressure is also directly proportional to number of molecules per unit volume striking the wall. Number of molecule per unit volume striking the wall. Suppose the molecule in the bulk are attracting the molecule which is striking on the wall of the container. They are attracting it and they are reducing its pressure, say by 2 Newton per meter square. So pressure of one molecule is reduced by 2 Newton per meter square. Had there been 2 molecules which are striking, the total decrease would have been 4 Newton per meter square. Had there been 3 molecules which are striking on the wall of the container, the decrease in pressure would have been 6 Newton per meter square. So more the number of molecules which are striking on the wall of the container, more will be the decrease in the pressure. So decrease in pressure is directly proportional to number of molecule per unit volume in the bulk, and decrease in pressure is also directly proportional to number of molecule per unit volume striking the wall of the container. See, number of molecule per unit volume is what? Density. So what we can say that decrease in pressure is directly proportional to density square. The first one is density, number of molecule per unit volume in the bulk. The second one again is a density, that is number of molecule per unit volume striking the wall of the container. That means the decreased pressure is directly proportional to the square of density. We know that density is inversely proportional to volume. So in this case, I can write decreased pressure is inversely proportional to the square of volume. If I have to remove proportionality, I will add a constant. So I can write decreased pressure is equal to A upon V square, where A is constant for a gas and it has got different value for different gases. A is actually the measure of attractive forces among the gas molecule. The attractive forces among CO2 molecules will be more as compared to hydrogen molecule or helium molecule, because their molecular mass is lesser, so their attractive forces are also lesser. Van der Waals forces, they are lesser. So different gases, they have got different value of A, and for a particular gas this A is constant. Now what we'll do, we'll put this value in the above mentioned equation, that is in this equation. So the correct pressure becomes, the actual pressure becomes observed pressure plus A by V square. That means if I put the pressure and volume equation, initially we had PV is equal to RT for 1 mole of a gas. Now after correction, it will become P plus A by V square into V minus B is equal to RT for 1 mole of gas. However, for n number of moles, we had PV is equal to nRT. Then this equation becomes P plus AN square by V square into V minus NB is equal to nRT. So this is the van der Waals equation for n number of moles. My dear students, as you can see, here we have got number of molecule per unit volume, that is density square. Density is number of moles per unit volume. So what I am writing? Volume square. Here I am writing volume square because by default I am considering that the number of moles are 1. That's why I have written 1 square. The square of 1 is always 1. Had the number of moles been n, I would have written n square by V square. So in that case, the density square would have been n square by V square. That's why here I am writing it is n square by V square. So PV is equal to RT, that's for 1 mole. Then the van der Waals equation is this. And when we have got n number of moles, then the van der Waals equation is this. So this is van der Waals correction and this is van der Waals equation. Next we'll move on to the liquefaction of a gas. In your textbook, this is the last topic which is given. So I'll wind up gaseous state by this, but later on definitely I'm going to add one video of Maxwell distribution of velocities, which is not given over here, but it is quite important topic. Maxwell distribution of velocities. In that we are going to study about root mean square velocity, average velocity and most probable velocity. Also we are going to talk about ideal gas equation according to kinetic molecular theory, KMT. But the topic now which we have got is liquefaction of gases. So we'll see liquefaction of gases. Suppose I have a cylinder and this cylinder is fitted with an airtight piston. In this I have got a gas and we want to liquefy this gas. See, as far the liquefaction of a gas is concerned, a lot of research is done in last around 30-40 years on liquefaction of gases. Because liquefied gases, they are used as propellant for rocket engine, cryogenic engines, liquid hydrogen, liquid oxygen. How to liquefy a gas? Well, if we want to liquefy a gas, what we can do, we can decrease its temperature. By decreasing the temperature of the gas, we are actually reducing their kinetic energy. The gas molecules, they are in continuous motion. They have got a lot of energy in them. So they are in continuous motion. They have got large amount of kinetic energy with them. When we decrease the temperature, their kinetic energy decreases and they start coming closer to each other. And the state changes their state from gaseous state to liquid state. So one way of liquefying a gas is by decreasing their temperature. The second way is by increasing pressure. If we increase the pressure, if we bring them close to each other, then we have to do some effort. We have to increase pressure up to a certain extent. We'll bring them close. But after that, van der Waals force will bring them more close to each other. So liquefaction of a gas can be carried out by increasing pressure also. So two ways I have told you, that either by decreasing temperature or by increasing pressure. The third way is very important, and that is by the application of both. You decrease temperature, you increase pressure. So neither you have to decrease temperature to a larger extent, nor you have to increase pressure to a very large extent. So this is how you can liquefy a gas. Out of these two factors, that is temperature and pressure, temperature is considered to be a prominent factor. A gas cannot undergo liquefaction above a particular temperature, howsoever high may be the pressure. That temperature is known as the critical temperature. For example, for CO2, carbon dioxide, the critical temperature is 31 degrees Celsius. So if you got CO2 at say 32 degrees Celsius, you increase as much as pressure you want. CO2 will not undergo liquefaction. So above 31 degrees Celsius, whatever may be the pressure, CO2 will not undergo liquefaction. So the critical temperature is 31. So what is critical temperature? It is that temperature at or below which a gas can undergo liquefaction by increasing pressure. And above that, the gas will not undergo liquefaction, howsoever high may be the pressure. Next is critical pressure. We represent it by PC. Now suppose here in this cylinder, I've got CO2 at 31 degree Celsius and I'm increasing pressure. 1 atmosphere, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say, this is purely an example. Say, at a pressure of 10 atmosphere, CO2 is undergoing liquefaction. That means it can undergo liquefaction not only at 10 atmospheric pressure, but also at 11, 12, 13, 14, but not at 9 or 9.5. So the minimum pressure required at critical temperature to liquefy a gas is known as critical pressure. So critical pressure is the minimum pressure that is required at critical temperature to liquefy a gas. Next we have critical volume. That is VC, critical volume. Critical volume is the volume occupied by a gas at critical temperature and pressure. So this is all about liquefaction of gases. And these are the topics which are given there in your textbook in gaseous state. As I told you that some of the topics definitely I'm going to add them because without that the knowledge is incomplete. This is all for today's class. This is what we were supposed to do. We have finished up with the gaseous state. In the next class, I'll be taking the liquid state and I'll teach you something about surface tension, viscosity, laminar flow, coefficient of viscosity, boiling and evaporation. This is what we'll do in the next class. But before ending with the lecture, again the same thing. Please do subscribe this channel so as to get all the notification and all the lectures on time. If you have any doubt anywhere, you got my number on the screen. Kindly send me a message so that I can revert back and I'll send you the answer of that question or that doubt. And I can include your doubt in my live streaming whenever I'll be taking a doubt removal session. So that's all for gaseous state. And thanks for watching my video. Thanks a lot.